Okay, great. So in the last class, we have started. We have briefly discussed lithography process steps. Okay. So let me. In lithography process step, we have seen that the optical lithography using UV light is the most popular one, and it is easier to use batch fabricated device out of it. By batch fabrication, I mean you can write several devices in one go by exposing UV light. And we have seen that there are different techniques like contact printing, proximity printing, and then later on projection printing came into picture. So apart from optical lithography, there we have also briefly discussed e-beam lithography. In e-beam lithography, instead of UV light, we have used electron beam. And the reason we need electron beam, because electron beam wavelength associated with electrons is much lower than that of the UV light we have been using as a source. So naturally we managed to get much higher resolution of the feature size what we have, what we can write through e-beam lithography. Okay. So e-beam lithography will give you higher resolution, but the issue is with e-beam lithography, and also another advantage of e-beam lithography is you don't need mask. In UV lithography, obviously you need mask, you need to write mask separately and use that mask. Mask is nothing but some opaque and transparent places depending on your design, and this mask usually made on chrome glass. But this mask is not needed in case of e-beam lithography, because in e-beam lithography you write your design in a CAD software and use that to control the motion of the electron beam when it is incident on the surface of your substrate which contains photoresist, right, or electron beam resist. So this is what we have discussed, and we have also discussed in e-beam lithography also, although you get much higher resolution, maybe few nanometer or few tens of nanometer, but the thing is it is a very slow process. So industry doesn't go for e-beam lithography. E-beam lithography is more for the research purposes, to develop a very tiny structure and see their performance, right? Now the thing is, we will discuss another lithography technique which is known as double pattern lithography today. Okay, so we will discuss double pattern lithography. My pen is still doing that. Okay, so in UV lithography, that is the optical lithography, there are several sources of lasers we use, or UV source we use. One of them is ARF, that is argon fluoride. Okay, that has wavelength around 193 nanometer. But even with this wavelength of UV source, you probably will be able to write a few hundreds of nanometer, okay, on the higher side, maybe just below sub micron, okay, just below micron, 1 micron range, simply because we did mention that there is diffraction. So due to diffraction, light will bend and reach the darker part of the or the opaque part of the photoresist, right? So with this UV source, okay, what people did, people managed to do various modifications. One of the modification they do is known as immersion lithography, okay, immersion lithography. In immersion lithography, I'm not sure you have heard this or not. In immersion lithography, you have a lens system, which is the case for all projection lithography. So there is a lens system, and of course there is a substrate, okay, and in between this lens and substrate you have your you put water, okay, so you put water or you have a column of water, okay, instead of air. So this is your lens, this is your substrate, and the column of water, okay, whose refractive, we know refractive index of water is around 1.44, okay. So with this you manage to get much higher resolution if it is air here, okay. So this is immersion lithography. These have been heavily used in commercial foundry. um, Obviously using water is a challenge and all that, but what I want to say is with this you manage to reduce the or manage to improve the resolution much more. So even below 100 nanometer writing is possible with this technique, okay. But if you go below like 45 nanometer or so, the feature size, then it is very difficult to write with only this using immersion lithography. Now what people usually do, if you go for this such a low such high resolution or such low feature size, okay, there is another technique which is there for several years now, which is known as EUVL, that is extreme ultraviolet lithography, okay, extreme ultraviolet lithography. So in this you the source is around 13 nanometer, okay, the source you can use is around 13 nanometer, uh, but to be honest this particular technique is not yet available commercially. There are uh, some equipment was made were made for research purposes, simply because there have been various challenges to use extreme ultraviolet lithography, because in this range lens basically absorb the UV light, so you can't use lens, you have to use very polished mirrors to achieve such lithography. You need several set of mirrors and so on and so forth. So it has been very challenging, although it has been there for I think more than 2 decades, this technique, and it's not easy so far to develop EUVL, that is extreme ultraviolet lithography, for commercial purposes, okay. But with this you can definitely reach sub 10 nanometer regime, okay. Now the thing I would like to discuss today, so this is not commercially available, this is commercially heavily used, have been heavily used This has been heavily used, but the thing is you can't go, I think below 45 nanometer is difficult with this. Okay, below 45 nanometer is difficult with this technology. So that the technique I would like to discuss today is known as double pattern lithography. Now this double pattern lithography is what is the concept? The concept is you write using your lithography system, you write features. Okay, say I'm writing I'm writing lithographically these lines. Okay, now so say the pitch is x here. Okay, now what we can do, we can overlay sorry we can overlay lines. Okay, so we write red lines with pitch x, then and we overlay another set of lines, say blue lines. Okay, of same pitch, say x. So you see, but the resultant pitch will be x by 2. Okay, so this has pitch x, this has also pitch x. Okay, but you see here the resultant pitch is x over 2, right? This is basically double patterning. Now there are different double patterning techniques. For example, litho LELE is one double patterning technique, which is known as litho H, litho H, LFLE, litho freeze, litho H, then SADP, sorry, self-aligned double patterning. So these are different techniques of double pattern lithography where all where all I am trying to do is allow double pitch density. Okay, allow double pitch density. So one of the crucial thing in this is known as overlay. What is overlay? Overlay is can be defined as the positional accuracy with which a new lithographic pattern prints on top of the existing pattern on the way. Because we have these red lines, okay, and then we write set of blue lines, okay, on top of, not exactly on top, but while the red lines existed, we have written these blue lines. So overlay is the positional accuracy with which this new set of lines, that is the blue lines, okay, we are printing on top of existing pattern on the wafer. So we have printed blue line while the red line already exists. How accurately we can print the blue line is basically known as overlay. Okay, so this double pattern lithography, the success of double pattern lithography depends on how accurately you can overlay. Okay, overlay the second pattern on top of the first pattern, right? So there might be different kinds of errors, uh, maybe rotational error, rotation at an angle uh, theta, okay, that can be one error. So the second the blue lines we are printing might not be exactly parallel to the already existing line, so it might be a little bit tilted by an angle theta, sorry. uh, there might be shift in x and y, okay, positional shift. It might go this direction or it might move this direction, okay, or vice versa. Oh, so then there might be translational error. Translational shift, okay, uh, translation of entire field shifted in x and y by delta x and delta y times maybe, okay. There might be relative magnitude error, right, relative magnitude error. So instead of exactly same area, it the size of your overlay pattern might be a little bit different, okay. So there might be say delta mx or delta my in x and y direction respectively. So there can be different kinds of error when you overlay pattern on existing patterns. So it might be rotational error, it might be translational error, it might be error due to relative magnitudes and so on and so forth. So overlay control defines the control of the pattern to the pattern alignment. Overlay control has become even more critical now because the combination of increasing pattern density and innovative techniques such as like double patterning and 193 nanometer immersion lithography creates a novel set of pattern based yield challenges at 45 technology node and below, okay. So as I said, in double pattern lithography, what we are trying to do, we are trying to overlay new patterns on top of the existing pattern using that same immersion lithography technique, which has become very important in modern days lithography. Uh, and we can achieve like sub 100 nanometer writing very accurately with immersion lithography. Now, using immersion lithography and using this overlay, we can achieve a double pattern lithography technique, which through which we can go even below 45 nanometer or so, right? So as I mentioned, there are different, we will not discuss how accurately or in which way we can overlay things, okay, that part I will not discuss here. But what I want to tell you, how this litho etch or litho fridge litho etch, self aligned double patterning, all this technique works, okay. So that part we will elaborate. To some extent this we have discussed in our FinFET fabrication, but let me discuss it more elaborately so that it will be clearer to you. So these three techniques, litho etch, LE, LF, LE, and SADP, these three techniques we are now going to discuss in more detail. Now, this first we will start with LE technique, that is litho etch, okay. In this technique we step 1 is L stands for lithography, okay. So step 1 is lithography 1 or litho 1, okay. uh, so how to draw this? Difficult to draw in 3D. So let me try. Say this is my silicon, okay. This is my SiO2. So this is my silicon nitride, okay. And on top of this, what I did, we created resist pattern, okay. So resist pattern, say resist pattern looks like this. Don't draw it because uh, first you see, then you can draw later on if required. So I put resist, spin coat it, and then I have uh, write a pattern, okay. um, So this is my pattern. So these are my resist. I have used the resist. Okay, use UV lithography or immersion lithography to write these resist patterns. Okay, now what I have done, I etch. I etch uh, so that the first pattern is on the hard mask, that is silicon nitride. Okay, so the second step is H1. So litho 1 is done. In the litho 1 I have spin coat photoresist, and write these red lines are resist pattern. So these red lines I should have written it with red, resist pattern. Okay, right. Now what I am trying to do now, I am trying to use this resist pattern to write on SiN, that is silicon nitride. So I basically, how I am doing that, I will etch this silicon nitride. Okay, so this step is known as H1. Okay, litho 1 H1 LE. So here also if I write it, let me just draw the 2D view, because I will struggle with this 3D view and it will take quite a long time. So I apologize, but you can see the 3D view in the note, but let me draw the 2D view. That will be easier for me to draw, easier and quicker. So this is my silicon. Okay, and this is my silicon dioxide. Where is the cursor? Yeah, here it is. So this is my SiO2. So on top of SiO2, as I said, I have etched silicon nitride. So I end up with silicon nitride only here. Right, because here there was resist, I have etched the rest of the part of the silicon nitride, so this part I have removed. Okay, so I have left with the first pattern etched into the hard mask in silicon nitride, right. Then I will do litho 2, right, litho 2 LE. So the step 3 is basically litho 2. So in this step, what I am trying to do, I will deposit resist and again write the pattern. Okay, so again a second resist pattern is overlaid onto SiO2. Okay, a second resist pattern is overlaid onto SiO2. So now what will happen, we have we have this is my silicon. Oh my god. Yeah, so this is my silicon. uh, Silicon dioxide, silicon nitride, and in there I have again deposit resist or spin coat resist, and we have written a second pattern using those on those resist. Okay, so I have a second litho step which gives me, this is my resist. Okay, I have deposit resist and write a pattern on it. Okay, now what I am going to do, I am going to do another set of etching. H2. In H2 what we do, again we start with, let's draw from the beginning. We have silicon wafer. Okay, and on the silicon substrate we have SiO2, but here etching is done on the SiO2 using both the patterns together. So etching is done using SiO2 with both the patterns together, right? So if you etch SiO2 with both the patterns together, then you will have like, sorry, right? You have etch SiO2 with using both the patterns together. So there you will have uh, you will have uh, you see you will have uh, silicon nitride here, you see, right? Silicon nitride. So you use both resist pattern and the silicon nitride pattern, both the pattern as mask and etch SiO2. So you remove SiO2 from other places. Only the places where resist and the silicon nitride is there, there only your SiO2 remains. In the rest of the places, SiO2 you etch out. So this is your silicon nitride. You see, this is your silicon nitride, right? These are your silicon nitride. Now what you can do depending on your, so if you look now carefully, it has your pitch is now x over 2. Okay, here pitch was x Here pitch was x, now it is x over 2, right? So you increase the density, you double the density. So if the you can use a washing step to remove SiN, okay, if it is required to wash out or to remove silicon nitride. So this is a pattern on SiO2 is now twice that of the density of the original design, right? Density of original design. So this was our original design, and in the SiO2 you are getting a design which is double the density of our original design. So this is a way one can double the density of the pattern, but the number of steps increases. 4 steps you see: litho 1, H1, litho 2 and H2, okay, which you can simply get away with in conventional lithography system. You can simply get away with 2 steps, litho and H, right? Here you need 4 steps. In fact, you need 5 steps if you want to remove your silicon nitride layer. Okay, right? Uh, you remember we have this silicon nitride layer uh, in our FinFET design, right? Silicon nitride and silicon oxide layer. So this is effectively a 5-step process if you basically want to remove silicon nitride. Now, so and also of course another concern is your overlay, right? Now the next technique is known as I told you, the next technique is known as litho fridge litho etch. So second double patterning technique is known as litho fridge litho etch. Okay. So here also let me just draw the cross-sectional view, the 2D view. I don't want to draw the 3D view. Okay. Here also I have like silicon dioxide. I mean silicon and silicon dioxide. Okay. So let's start with step number 1, that is litho 1. Okay. In litho 1 we will have like silicon substrate or silicon wafer. On silicon wafer you grow or deposit your silicon dioxide. Where is the cursor here? So you first pattern one set of lines using one layer of resist. Okay, so you pattern one set of line using one layer of resist. So say this is my pattern using the resist. Okay, so this is my resist, right? Then the second step is freezing. Okay, so you freeze this design. You have to freeze this design. So again what you do, let me draw it once more. So we have our silicon substrate, we have our SiO2, and And on the SiO2, what we do, we have this pattern, we have this already pattern, like in from litho 1 we have this pattern. So let me draw the pattern once more. And so now we coat with a new resist. Okay, so because we want to freeze this design, so we coat with a new resist. So we coat with a new resist. So this is resist 2. Okay, so we coat with a new resist, so that the whole purpose is to freezing the existing pattern, okay, without etching it. In the earlier cases we etch these patterns, right, using these patterns. So then we so in step 3 what we do, so that is another litho step. So litho 2 step, okay, or second lithography step. This will give a pattern on resist 2, okay, but resist 1 pattern will remain intact because of freezing. Okay, so we have freeze this pattern, we will write a new pattern on resist 2. Okay, so if we write pattern on resist 2, uh, is there a way to take this? I'm just uh, no. Is there a way to copy this? Okay, let me try. Then I don't have to draw it again and again. No, it's not. What about we just remove it? So let me, can I copy this? Can I copy this? Can't. Okay, I can't, right? I can't copy this page. No, I can't copy it. Can I copy this? Okay, let's do that. I can't copy it. Right. So what I'm trying to do is trying to uh, copy a part of it anyway. So this is my silicon substrate, my SiO2, and my SiO2 I will give. I am patterning now resist 2, okay, keeping the resist 1 intact. So if I do that, I will have uh, these are my resist 1 pattern, and then sorry, is my cursor? Okay, so this is how I'm writing using these are resist 2. Okay, and this is resist 1. Keeping resist 1 pattern, I am writing pattern on resist 2 using this litho 2 approach. Okay, now I am etching both the patterns are etched together on the hard mask material, say SiO2. Okay, so this is, if I now etching. Okay, so in this what I have done, this is my silicon substrate, and on the silicon substrate I have etched SiO2 using both resist 1 and resist 2 pattern. Okay, so if I do that, then you see we have both. So you see we have written the pattern on SiO2. Okay, this has double the density. So pitch is, here pitch was x, here pitch you see x over 2. Okay, compared to LE, it has 4 process steps. However, the challenge is to resist selectivity. Is resist selectivity, because two different resist you need to use, and overlay is more challenging because you have to keep one freezing and the other one you then etch to make the pattern and all that. Okay, I mean you then use the litho 2 to make the pattern and all that. So this is litho fridge litho etch technique. Okay, and third technique which I would like to discuss now is known as SADP. Okay, this SADP technique probably we have used when we were discussing uh, FinFET. So this is SADP, that is self-aligned double patterning. So self-aligned double patterning technique, uh, in this technique you want create dummy pattern. Okay, also known as mandrel. Dummy pattern is known as mandrel, and it is like mold. Okay, mold material to form the pattern. Okay, and then you remove the mandrel, right? Now, so let me draw it once more. So the step 1, sorry, it's my pen is giving me a hard time. If I look at the screen, I can't see my pen anyway. So yeah. So in step 1, what I do, I have silicon, I have SiO2, okay, and on top of SiO2 I have made a mandrel dummy pattern. Okay, I have a dummy pattern made of mandrel. So this is my mandrel dummy pattern. Nothing but then what we do, we need to grow sidewalls around this mandrel. For this, what we do, we deposit conformal layer of silicon nitride. What is conformal layer? Conformal layer is a layer which is basically follow the shape of this mandrel. Okay, that is basically conformal layer. So we deposit a conformal layer of dielectric silicon nitride. So in the next step, what we do, let's draw it once more again. This is a pain, drawing it the same thing several times. Okay, so this is my silicon. Okay, this is my SiO2. This is my mandrel or dummy pattern layer. On top of this mandrel, what I have done, I have deposited conformal layer of silicon nitride. Which one is silicon nitride? This one. Okay, so I have deposited conformal layer of silicon nitride. So this is my conformal layer of silicon nitride. Okay, so then you edge back. Okay, you edge back. So when you edge back such layer, you tend to etch the horizontal portion, leaving the vertical portion. Okay, so if I just zoom in one of the mandrel, okay, if I just zoom in one of the mandrel, so say this is my this is the mandrel. Okay, let me etching. So it will be like this. But if you look at the silicon nitride layer, the silicon nitride will become, so the silicon nitride was initially like this. Okay, here you see, now it due to etching it will become like this. So it will remain in the vertical portion, but rest of the portions it will be removed. Okay, so dielectric layers are removed except the side walls. So it is SiN is there only around side walls, right? SiN is there only around side walls. So then you strip the dummy pattern. Okay, then you strip the dummy pattern. So if you strip the dummy pattern, okay, what is the to strip the dummy pattern, okay. So here again, let me draw once more. This is my silicon. This is my SiO2. And I have removed this dummy pattern mandrel. Okay, so what I am having now, I am having my only SIN sidewalls. So I am having SIN sidewalls. So I have removed my mandrel. So mandrel was initially here. Okay, I have removed the mandrel. In fact, okay, I have removed the mandrel, and I am ending with so there were initially 4 mandrels, right? Okay, so I have removed with I am leaving with this SIN pattern. So you can etch, one can etch this I can't see my pen. H2. Okay, so here you etch SiO2. You etch SiO2 using this masking layer, okay, of SiN. Okay, using this special layer SiN, you etch hard mask SiO2, right? So this is SADP pattern. This pattern, if you remember, we discussed during our FinFET fabrication. Now the advantage of SADP compared to that of other two is, you see here only one lithography step is required, right? Only one lithography step. That is advantageous because litho is the most expensive step in the process steps, right? So reduction of one number of litho step is an advantage. And also overlay is not required. That is another advantage here. You see, overlay is not needed because only one lithography steps. Overlay is not required here in this particular. But you see here, the pitching is different. Pitching is different compared to earlier ones where the pitching is exactly x/2, right? Pitching density becomes double, but here pitching is different. Pitching is x1 and x2, right? Because we are not exactly following. So this is a mandrel, this is a mandrel, but pitching here is different. Okay, you see. In fact, Intel first when published their FinFET structure around 2010, 2011, people found that their pattern has different pitches. Okay, this is probably, I don't know, it might be, then people started arguing that it might be due to overlay error, or it might be that they were using SADP. Okay, SADP pattern, right? Now this is we see that we have like double patterning our design, right? But along with double patterning, we can have even much more using the same design. Okay, for example, we can have triple patterning, we can have 4 times patterning, 8 times patterning, and so on. Now double patterning gives two times the pattern density that we have seen. Now what about 3 times pattern density? Okay, 3 times pattern density. Can we achieve with this similar approach? Let's check. Okay, so let's our mandrel. Let's draw our mandrel. Mandrel. Then we have defined our spatial layer. Okay, and we have used our this thing, our etching, back etching, so that we so say this is our one spatial layer which we managed to etch. Then we use another set of spatial layer. Okay, second set of spatial layer. Okay, Then what we do? We remove the fast spacer material. Sorry, I can't see this. See my pen. Is the cursor? Yeah. So I remove. If I remove this fast set of spacer layer, okay, that is made with red, so you end up with so we have removed the fast set of spacer layer, and you see now we have used now this uh, pattern density is increased 3 times. Okay, pattern density has increased 3 times. Here I have removing the, where is the cursor? Removing fast spacer layer. Right? So similarly, you can do like 4 times pattern density increment, 8 times pattern density increment, and so on. Okay, but the thing is whether you, I mean, through this you can keep on you keep on following Moore's law. So we can go to 22 nanometer, 14 nanometer, 10 nanometer, 7 nanometer, and so on. Okay, because we have this double pattern lithography technique through which you can increase the density of the pattern. Okay, but the thing is your steps will increase, your cost will increase, your complexity will increase, and so on and so forth. So with this I am stopping this double pattern lithography discussion here. If you have any queries, please raise your hand. If you have any doubt, please raise your hand. Right. So you don't have any doubt. Okay, so let me start with another topic now, which is single electron transistor and Coulomb blockade effect. single electron transistor and Coulomb blockade effect. Just give me 2 minutes. I'm just coming from washroom. Give me 2 minutes, okay? Please. Thank you. I'll be back in 2-3 minutes, okay? Yeah. So let's start again. So uh, we have been discussing single electron transistor and Coulomb blockade effect. Okay. Now, so this is a different kinds of device in nanoelectronics. This device is not in the market. This is still in the research domain. Okay. But this is a very important concept which might lead to some device in some days. Okay. Now, as the name suggests, this single electron transistor, where we are talking about a transistor in which we can manipulate or control the movement of even a single electron, right? So let's consider a quantum dot. quantum dot. I have two leads to access this quantum dot. What is quantum dot? Quantum dot, you remember we talked about quantum well, okay, during our Schrödinger applications. We talked about infinite potential well, finite potential well. Those are quantum well, right? And we have seen that electron is confined, okay, an electron can have only specific energy levels, and it is confined within that well if it is infinite potential well. If it is finite potential well, then electrons have some finite probability to remain stay even outside the well. But in general purpose, we can say that electron is confined in that potential well. Now that is one dimensional potential well we have talked about. But if this potential well is in all three directions, okay, so then the electron will be confined in all three directions. Now if that potential well is very tiny, like a dot or a particle, okay, then this particle or the dot is known as quantum dot, where the energy is confined in all three directions, or the particle is confined from all three directions, okay. So here we are considering a quantum dot, or you can say quantum island, which is separated from two leads via quantum barrier. So these are tiny barriers. These are tiny barriers. So this quantum well or quantum dot. So this is my quantum dot or quantum island. This is separated from the two leads by quantum barrier. Okay. We will see that a significant amount of energy is required for a few electron or even a single electron to transfer from lead to quantum dot or vice versa. We will see that a significant amount of energy is required to transfer electron from lead to quantum dot or vice versa, quantum dot to lead, even for few electrons or even for a single electron to transfer. Okay, it can be shown that this carrier flow, or basically carrier flow means current flow through the material, could be prevented if the capacitance of a particle was sufficiently small. By sufficiently small, I mean of the order of attofarad. Attofarad means 10 to the power minus 18 farad. Okay, if the capacitance, it is possible to show this carrier flow or current flow could be prevented if the capacitance of the particle was sufficiently small, of the order of 10 to the power minus 18 farad. Okay, or less. Let's start from our basic observations. In a capacitor, in a simple capacitor. So I have two conductors separated by a dielectric. Okay, this is a capacitor, right? Two conductors separated by a dielectric is nothing but a capacitor. So two conductors are separated by an insulator. In that case, the charge and voltage is proportionally, we know, right? Q is proportional to V. U is equal to C into V. Okay, and the electrostatic energy stored in the capacitor E is equal to half CV square or Q square over 2C. So this is the energy required to separate charges initially upon applying potential across the inductor, across the conductors, right? We know that simplest capacitor is formed when two parallel plates of area, say A, and a distance or separation between the plate D is this, right? If we consider epsilon is epsilon naught, that is okay, then we can form, we can get some number. In my note I have a table with some number, say A, that is the area of the capacitor, nanometer square, D, that is the separation of the two conductors or the conducting plate, that is D, nanometer, C is in farad, and delta E. What is delta E? Delta E is the change in energy due to transfer of a single electron through the capacitor. Okay, so that we are going to see. So say this is 5 square. This is 2 nanometers. So if you calculate C using this formula epsilon naught A over D, then C you will get 1.1 into 10 to the power minus 19. Corresponding delta E is 0.73 electron volt. What is delta E? Let me repeat it once more. Change in energy due to transfer of a single electron through the capacitor. So I have some other values. So you see that in the first case here, okay, in the first case, the capacitor is very small, of the order of 10 to the power minus 19, and transfer of a single electron requires appreciable amount of energy. Transfer of a single electron requires 0.73 electron volt. You see, that is appreciable amount of energy. Whereas in case 3, okay, the capacitor is of the order of 10 to the power minus 13 farad. That is comparatively large compared to this one, right? Compared to first case. In this case, the change in energy due to transfer of a single electron is negligible. Change in energy due to transfer is negligible. So it is this sensitivity to transfer of an extremely small amount of charge that allows the possibility of so-called single electron precision devices. It is this sensitivity, you see, because when you are reducing the capacitor value, okay, you need significant amount of energy to transfer a single electron. Okay, so in other words, you can make a device where you can control the movement of even a single electron. Okay, so it is this sensitivity to transfer of an extremely small amount of charge that allows the possibility of so-called single electron precision devices. Now, We can extend the discussion a little bit more before we close this session today. Let me introduce you the concept of Coulomb blockade. Okay, so the initial electrostatic energy stored in the capacitor is EI, that is Q square over 2C. Initial electrostatic energy stored in the capacitor. Now suppose a single electron of charge QE tunnel through the insulating layer from negative terminal to positive terminal. Okay, so such that the top plate, which is the positive terminal, top plate we are assuming positive, so top plate, so it is going from negative terminal to positive terminal. So the top plate charge becomes what? Top plate now has charge Q plus QE, and the bottom plate minus Q minus QE, right? So the final electrostatic energy, say I am writing EF, Q plus QE whole square over 2C. That is Q square over 2C, Q plus QE over 2C. So this is the final electrostatic energy, that is after transferring one electron from negative terminal to positive terminal. What I am trying to do now, I am trying to achieve a concept of Coulomb blockade. So what is the change in stored energy? Change in stored energy delta AC is equal to EI minus EF, right? EI was the initial energy, EF is the final energy. So if you do that, this is Q square over 2C minus Q plus QE square over 2C. This has to be, so this process of transferring electron from negative terminal to positive terminal, this can only happen if it is energetically favorable, right? So this has to be greater than 0. So higher energy to lower energy, if it can move, then only that phenomena will take place, right? That is from the laws of physics. So that has to be greater than 0 to make the phenomena energetically favorable. So if you use that, you can simplify it and you will see that Q will be greater than minus QE over 2. Okay, so the condition for tunneling to occur. So the corresponding voltage, what is the corresponding voltage? Voltage should be greater than minus QE over 2C. Okay, we can repeat the above calculation for a single electron transfer for opposite polarity. So positive terminal to negative terminal. If it goes from positive terminal to negative terminal, we can have positive terminal to negative terminal. If it goes, then we can have Q square over 2C minus Q minus QE whole square over 2C. This should be greater than 0 in the same argument, following the same argument. And this will give you ultimately Q greater than QE over 2, and the corresponding V is QE over 2C. Okay. So you see tunneling current will only flow when a sufficiently large voltage. What is that sufficiently large voltage? Mod QE over 2C exists. Right? See here minus QE over 2C, this is plus QE over 2C. So tunneling can only occur if you have a sufficient amount of voltage which is mod QE over 2C. Okay, exist across the capacitor. This is known as Coulomb blockade. So without this voltage, there will be no tunneling of even a single electron between those two the plate of the capacitor. And what is the corresponding energy? Energy is QE multiplied by V. That is the corresponding energy required. So the corresponding, this is charging energy of the capacitor, which is nothing but QE square by 2C. Right? So we can plot I over V. Okay. And this is your mod QE over 2C. Okay. Hence Coulomb blockade is not evident if the capacitor is of large size, because the charging energy is very low. In that case, we have seen in the table here, if the capacitor is value is comparatively large, we will not be able to get Coulomb blockade effect because the charging energy is very low. Okay. Hence thermal energy. What is thermal energy? Thermal energy is kBT, right? Thermal energy kBT. So thermal energy is good enough for the electrons to tunnel. Right? kBT is, you remember, 25-26 millivolt when it is at room temperature. So that should be good enough for the electron to tunnel. So for large value of C, to get Coulomb blockade effect, we have to reduce the temperature. Right? Because this kBT is good enough to allow the electron to tunnel. So for large value of capacitor, you need to reduce the temperature to see the Coulomb blockade effect. Okay. So with this, I am stopping here today. Okay. Do you have any queries? Any queries? No query. Is the pace okay? Was it understandable?
Yes, sir.
Okay, so let me, I will upload the note and you can see, you can go through the note, and if you have any doubt, you can ask me. Okay. Okay. So thank you very much.